In this video, we want to talk about rotational energy, and we'll take a look at it as we've looked at a lot of rotational systems. We'll first look at a particle and then try to extend it to a solid object rotating in a plane. Okay, so first I have, let's say I have some mass, and it is moving in a circle, and it has some velocity v tangent to the circle and some angular velocity omega. If I look at the kinetic energy of this particle, that kinetic energy is simply 1/2 mv squared, which is fine. How would I represent that in terms of my angular frequency, omega? Well, I know that omega is equal to v over r. That's tangential velocity. V is equal to omega r. So if I substitute that into my kinetic energy, I get 1/2 m omega r squared. So I rewrite this a little bit, 1/2 m r squared omega squared. And we see this right here is what we represented as the moment of inertia of a particle. And so I can rewrite the rotational energy as 1/2 I omega squared. Okay, and so really all I've done is rewrite our traditional kinetic energy for a particle in terms of our rotational the characteristics, our moment of inertia, our angular velocity. But this is now just the same kinetic energy. All right, so let's now extend this to a solid object. And so let's say I have now some disk. It's solid and it rotates around an axis in the middle. Okay, and so if I want to look at some small element of mass, which I'll conveniently call dm, a very small mass element. It's some distance r from the center, and this whole disk is rotating around. So let's find the kinetic energy of this small piece of mass. So this small piece of mass has a small piece of kinetic energy, which I'll call dk, and it's equal to 1/2 the mass, which is dm, times the velocity of the mass, which is v squared. That's just kinetic energy, 1/2 mv squared. Nothing unusual. I've got the dk and dm just to remind myself that it's a very small amount of mass, and so it has a very small amount of kinetic energy. If I repeat the same thing I did before up above, then this becomes a 1/2 r squared omega squared times the mass. And so then I can write the kinetic energy then is equal to 1/2 r squared, well, omega squared dm. I just sort of rewrote it here. Okay, so now what I want to do is I want to add up all the little masses everywhere in my disk. Okay, and so there's a mathematical representation of that statement. If I want to add up all my little kinetic energies, this is my mathematical statement of doing that. I add up all my little kinetic energies, and I get the total kinetic energy of the system. Now I want to add up all the amounts over here for all the little masses everywhere in my disk. Okay, so for each mass, of course 1/2 is a constant, but each mass is going to have a different r squared. However, each mass has the same omega squared. So I can pull the omega squared and the 1/2 out of this sum. I'm summing up all the little particles. So I get the kinetic energy is 1/2. Then what's left here, the sum of all the masses times their r is the distance each little mass is from the axis of rotation, then times omega squared, which I've pulled out of the sum. And so now I recognize that this is the moment of inertia of a solid object. Okay. And before we talked about representing the mass as a small area element or length element times a density and all of that, but we don't have to worry about this yet. I mean, this is sort of our original definition of the moment of inertia, and that's all we need to be able to recognize then that for a solid object, the kinetic energy of the rotating object is 1/2 the moment of inertia times the angular velocity of the rotating object squared. So, for example, if my mass over here was 4 kilograms and was saying it's rotating at an angular velocity of 2 radians per second, and let's say it had a radius of 2 meters, well, simple numbers here, then the kinetic energy, the total kinetic energy of this rotating object, which is the sum of the velocities of all the little mass elements, is then 1/2 the moment of inertia of a solid disk is 1/2 the mass, which is 4, times the radius squared, which is 2 squared, times the angular velocity squared, which is 2 squared again. And so I have lots of 2's and 4's. So here's 2 cancels that 4. So it looks like I have 4 times 4, or 16 joules of kinetic energy. Okay, so, well, that's simple. I want to now take this object, my disk here, my solid disk, and let's say this object is moving then with some velocity. And so I want to distinguish this now. This total, the object is moving, so its center of mass has some velocity. So this whole disk could be moving with as well as rotating. So in this case, our kinetic energy is going to have 2 components to it. The kinetic energy of the object rotating as well as the kinetic energy of the object translating, the entire object moving through space. Okay, and so before we just had objects moving through space, 1/2 mv squared, and then before we just had an object rotating. Now we want to combine the two. So it's useful to break it up into 2 components. So we have 1/2 times the total mass times the velocity of the center of mass squared. This is now, we'll call the translational kinetic energy, plus 1/2 the moment of inertia times the angular velocity squared. And so this is now, say, the kinetic energy of rotation. So now if we have rotating objects that could also be moving, when we look at the kinetic energy, we have to take into account both types of kinetic energy. So let's do a quick example, sort of the classic, or not even classic, just simplest example. We're going to take that same disk and we're going to roll it along the ground so it's rolling without slipping. Okay, and so we're going to take our same mass we had before. Mass is 4 kilograms. It has a radius of 2 meters, and it's going to be moving with a center of mass velocity of 4 meters per second. Okay, what is the total energy of this object? So I'm given its velocity, 4 meters per second, but its total energy is not just 1/2 mv squared, because this is a solid object. If it's rolling along the ground, it is also rotating, so I have to take into account its translational energy as well as its energy of rotation. Okay, so what is its energy of rotation? Well, we know it's rolling without slipping, and so we want to use that information. So first, we know then that the velocity of the center of mass is equal to, say the tangential velocity at any point at the edge of the disk. So at the edge of the disk, a point has a tangential velocity, and because the object is rolling without slipping, we know that the velocity of the center of mass is equal to the tangential velocity at the edge of the disk. Okay, well, we also know that the tangential velocity is equal to the angular velocity times the radius of the disk. The tangential velocity at the edge of the disk is equal to the angular velocity of the disk times the radius of the disk. So this now gives us a way to relate the center of mass velocity to the angular velocity of the object. Okay, so now if we want to go ahead and solve this problem, we can say, okay, our kinetic energy is going to have a translational term to the kinetic energy as well as a rotational term. And the translational term is just 1/2 the total mass times the velocity of the center of mass squared, plus the rotational term, which is 1/2 the moment of inertia times the angular velocity squared. So if this is equal to now 1/2 m, well, just v sum m squared, fine. And then 1/2, now the moment of inertia, if for a disk, for this solid disk, is 1/2 m r squared, and if the angular velocity is, well, it's, angular velocity is equal to the tangential velocity over the radius. That's sort of the definition, from the definition. But from rolling without slipping, this is equal to the velocity of the center of mass over the radius. I can substitute in, then, the velocity of the center of mass over the radius squared for the angular velocity. So now, let's simplify this a little bit. 1/2 m v center of mass squared plus, and so now I get velocity of the center of mass squared, r squared, the r's cancel, I get the 1/2 times 1/2, 1/4 times the mass times the velocity of the center of mass squared. Okay, and so then that becomes, I can add these together, and 3/4 mass velocity of the center of mass squared, and if I plug the values in for that, 3/4 the mass is 4, velocity is 4 squared, I should get, let's see, the 4's cancel, 16 times 3, 48 joules. Okay, and maybe I shouldn't have combined them. I'm not sure that's as useful. This is equal to, if I look at this term, I have of each of my translational and kinetic, I had 1/2 the total mass, which is 4, times the velocity of the center of mass squared, which was 4 squared, plus then this term, which was my energy of rotation, which is 1/4 the 1/4, I guess, times the mass times 4 squared. And so this term gave me 32 joules, plus this term, which is 16 joules. And so we saw that with this thing rolling, we had 32 joules of translational energy, as well as 16 joules of rotational energy, for a total combined amount of 48 joules. So when we have rolling objects and we need to know the kinetic energy, we have to take into account both the translational kinetic energy of the object as well as the rotational energy.